Hey, welcome. Oh no, wrong video. Yes, another draft physics video presentation. Comments first, I suppose. A couple anyway. Almost worthy subjects. I don't know. So first on the gravity video, Carmine says another factor to consider in regard to loss of height is that of muscle activity. I won't even bother reading the rest, but anyway, you're really not getting it. We're being pancaked by one force, the force pushing us up, because that's the one our body has to react to. The whole point is gravity can move you without bothering you at all, because it moves all of your pieces consistently. So everything moves. Nothing's left behind, so to speak, in the sense that it's very efficient at moving all of your matter. Not just the outside of you, not just pieces of you. It doesn't have to go through the matter to get to the matter, so to speak. And so it's the one we're always fighting, the one that's always pushing in this bad way, is just the one pushing us back against the earth pushing back. So that's the only force that has to go through your body in this uneven way, where there is any tension, or there is any resistance, or there is any need for the body to react in some way to compensate for the unevenness of the force, the fact that your feet are accelerating faster than your eyeballs. That's what your body has to react to. So in a sense, we're just being pancaked by that one force. That one force keeps, no matter what position we're in, it's going to keep spreading us out, so to speak, pancaking, squishing. And that's it. If it was all gravity, if it was gravity fighting back this way and gravity pushing this way, we would be, who cares? It just couldn't make a difference. It wouldn't affect us, because there would be no tension created. There would be no unequalness to our structure. Our head wouldn't feel different than our tail. There wouldn't be anything to compensate for. There wouldn't be any imbalance in our physical structure to compensate for. Okay, so that's probably enough said on it. So if you did exercises while you were lying flat, that would help flatten you more. I mean, the more you move, the more you're helping the flattening. So if I want to flatten something, the more I jiggle it, the easier it is to compress. So you're only helping the force by muscle activity. So if you have muscle activity and there's a force, unevenly pushing you up from your feet or your ass, you're accelerating its capacity to squish you. Okay, so the more you, it's just that idea. The more you shake something, that you're trying to settle, the easier it is to settle it in gravity. And so you're only helping the force by activity. So if you did your activity lying down, you would get taller. So whatever. All right, in regards to magnets, could an ice cube become magnetized? I don't know why you picked ice in particular, but whatever. What would prevent this from occurring? Well, it's all about the shape of a crystal, right? So that's what all this is. This is all about how atoms magnify each other's, any defects in them, any structural nuance. So all the materials that are magnetic, nickel, cobalt, I think, and iron, they're all right next to each other in the periodic table. So you can sort of understand that this is probably some kind of geometric thing. And it's like, I could draw a pentagon, right? I could make one almost. Not quite. And I could say that, okay, that shape of, the interior orbits of an atom, let's say, having 5 things in the interior orbit, would be a shape, that the rest of the orbits couldn't compensate for and turn into a circle. Okay, it would always be imbalanced. And so the atom, whatever the shape of the atom would be, would always have an imbalance in it. It would always have a little more electrons on this side and a little less on this side. And but if I go to the sixagon, and this So, but a septagon, the shape isn't enough of a, it's more balanced. The imbalance is spread. So there's one shape that can be compensated for, another shape can't be, in terms of making it circular, or making it inert. Having that shape be transferred to outer shapes, that have to balance to it, kind of thing. So the argument would be is that it's only in this little, like the Goldilocks zone for water, where it's frozen or it's a gas, and it's only this one place where it's a liquid, this one temperature, this one little temperature range. Well, there's only one little geometric range that actually creates polar polar atoms, that are innately polar. They can't be unpolar. And then the trick is that they have to be polar, and then you have to be able to stick those polarities next to each other in an arrangement where they're all going in the same direction. All their polarities are pointing in the same direction. And so that's sort of what's indicated, is that sort of happens when you run electricity through other metals, is that you polarize all the atoms in the same direction. You squish them, you stretch them, however you want to look at it. You misshape them all in the same direction. They all become polar in the same direction, and then they imitate what magnets do. Now, as I understand, water crystals, they're spherical. Their geometry isn't polar. So they can't really make a magnet, first because they don't have polar geometry, and let's say they even did, as I understand, they sort of do a ring thing, a circular thing, and that's what ends up trapping the water and all this other kind of stuff. So the crystal doesn't grow in straight line geometry. Instead, the geometry is based on, the circular crystals or something, some other shape. So that's why you can't make it into a magnet, is because the atoms aren't polar in the first place enough, and they don't arrange in one direction. They don't form crystals in one direction, oriented in one direction. And so they'd end up just like with magnets. If I take a bunch of magnets and I put them in a circle, I've kind of defeated their purpose and kind of destroyed how magnetic they can be, because I've got the poles all turned in different directions, and so there's no predominant north and predominant south, because all the atoms aren't pointing north and south. The atoms make the magnet. A big magnet is made out of little magnets, and water doesn't do that. I guess that'd be the simple answer. Alright, so it's a couple of subjects I'll move on to. I don't think there was anything else in this comment section really worth reading. Blah 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 blah. So this is some Ken Wheeler Nutter 20-20-20, pothead. How fascinating. 40, 80, 90, 60. I don't know what all that number crap means. So anyway, so it's just amazing. So this isn't a bad statement. It's just amazing that these science guys actually believe that merely feeling like you aren't being accelerated accounts to an insurmountable proof. What they think is a proof is sort of an argument that, this whole conversation is based on, is the fact that they think they have proven something, and that something's the most proven theory in the history of mankind, and all this other crap, and it's just such crap. But not understanding, nowhere in the physics, nowhere have I heard a single physicist account for the fact that there's a fundamental difference between a force that's affecting all of you and a force that pushes on some part of you. That they haven't gotten the getting hit with, say, 500 units of momentum, getting hit by a mattress with 500 units of momentum, are getting hit by a bullet with 500 units of momentum. Like, they can't figure out that one is going to be really effective at accelerating you, and one is going to be really ineffective because it's going to accelerate some of your pieces really fast and most of your pieces not at all. You know, that's so obvious. Alright, so anyway, so I did think of another thing on the interferometer that I wanted to include, so I guess I'll do some drawing and just, you know, because it's something I thought of a while ago, and it's a really important feature of understanding this whole mechanism of the reflected light and blah 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 blah, the whole function of the damn thing, and how no one else has done any of this analysis. I mean, they clearly just do it in this simplistic, well, it's sort of like the two-slit experiment. They just draw the waves and say it works when it really doesn't. You know, as I've pointed out, a beam splitter isn't a simple device. It's a complex device in many ways. It's not doing some simple, oh yeah, half of you just go this way and half of you go that way, no problem. It's just not that simple. And for none of them to concede it's just not that simple, that's just evil, wrong. Okay, maybe I'll pause because this will probably, I'll probably knock the camera over or something. Alright, looks like everything's working properly. Anyway, alright, so the interferometer, you know, it's just this simple idea. You shoot light in, one beam reflects, one beam goes through, you know, and then you send it back through, and one beam goes through, and one beam reflects back, and you have two beams. So all we really want to talk about is those two beams. So let's talk about them when they come out, you know, as they're coming out. So one of them has, you know, went through the little openings and has been spreading its entire trip. And at the last reflection, it's still spreading. So that's what it's still doing when it's coming out of the last piece of the machine. The other beam hasn't been spreading the whole time, and so now it only starts to spread now. So it's going to create another little cone of light in here. And so the idea is that both of them are spreading. That is, the photons are moving in space and they're separating from each other in a sense, because they're on trajectories. They didn't go straight lines through this whole experiment. They went bent lines through the experiment. At least this last beam did at the last minute. And so both of them, in a sense, you could argue, are doing this thing. You know, like the light comes out, and some of it, right, is going to be, like especially this beam, some of it, right, it's all going through little holes, little slits. So some of it's going to go this way, and some of it's going to go, you know, this way, and then some of it's going to go in, and some of it's going to go in. Okay, and this same kind of effect is going to happen to some of the light from this, is that some is going this way and some is going to go in, and this is the light that's going to have to meet, right? So we're really talking about these two. You know, this is that center of the pattern that does that, you know, where you have the rings, and this center, you know, blinks on and off. And what really is happening is this ring goes light, and then this one's dark, and this one's light, this one's dark, and what that's really happening is they're just reversing. You know, the one that was light is now dark, and the one that's dark is now light, as you're combining these two sources. Okay, and so you could see in the last video where I showed the action lab, you could see where, you know, he didn't line up the instrument. You have to sort of first line up the mirrors on the instrument, right? So you have these two mirrors, and you sort of have to make sure that they aren't canted in any way, you know, aren't crooked. Because if they're a little bit off, then these centers end up being all screwed up, you know. And so now you don't have the two focuses on the same location. What you're really doing is taking the ring, you know, you could see it in his, I'll just draw it because you could see it so obviously. I mean, obviously this is a conversation where people know something about this stuff. you could see that when he was looking at one light, he was getting the ring pattern, and then when he put the other light, the other source, when he opened the other source by opening that mirror, that the other source was doing this across the ring pattern. That's sort of giving you the example of one of these images is a really big image, okay, really big rings, and one of them is a very small one. And what you're really doing, you're first to line up the machine, you have to make this pattern with these big bars match this pattern. So you have to line up the mirror so they're both pointing, they're both perfectly vertical. So the light isn't being reflected up or down or left or right, because that's what he was demonstrating, is that he never calibrated the mirrors, never lined these two patterns up, because when you line them up, then you'll get a perfect little circle in the middle and you get these rings, because you have them both lined up, they both aren't canted in any way. So that's the key, the first step to doing this thing the right way. Now this still works in the sense that you're still going to have lines where you're crossing each other, okay, and you'll have brights, and you'll have, it'll just be a little messier, because you'll still have where the two are lined up, where the two are still in phase. And so you're really just doing, again, this adding sources, and as you add the sources, you multiply the amount of light you have by adding the extra sources. But anyway, so this is the pattern you're after, and this is what I found. So as soon as this focus, though, as soon as I do bend one of those mirrors just a tiny bit, just the tiniest bit of deflection in the mirror creates, a great deal of movement in this, and it changes this from on to off and on to off, because you're basically taking these two patterns and you're changing where they are so they're not lining up anymore. So you're changing where the alignments are, and that's what's turning it on and off. See, one of them's focus is here, and its rings are going here and here and here. So as that moves, you're changing where the ons and offs are going to be, because you've changed the two cones. So again, this is really just about matching two cones together that have stripes in them. They're wavelengths of distance difference. And I'm taking another cone, a smaller one, but it doesn't really matter, and it has lines on it, and I'm just pushing those two into each other. And you can sort of understand, though, if I tilt one of those, I'm really going to make a mess out of that, because I'm going to have all kinds of different places where it'll be, I might not be able to see it because it's going to be a dotted pattern, and the dots might be small enough that I won't see that I've screwed it up entirely, but I have screwed it up entirely. So anyway, so it's really important. That's all I'm saying, is this part of the experiment isn't so much about mirrors moving just this way. You also want to change the pattern. All you have to do is tilt the mirror this way or this way. All you have to do is create any change in the position of the mirror, and you change where this focus is, and you change whether the two are in focus or out of focus, whether the two are lined up in phase at the same location is completely dependent on the angle of these cones. And so when they're changing the distance of the mirror by turning a screw, that's moving their mirror, what they're really doing, because it's such an imprecise instrument, is they're doing this to the mirror. They're jiggling the mirror. They're tilting it. Okay, and so they're not really moving a millimeter of distance. That's not really what they did. What they really did was change the tilt of the mirror. So anyway, and that's why sound is so important, because sound is always vibrating. The surfaces, glass vibrates a lot, especially, but metals, anything's going to vibrate with sound, and all of those vibrations are essentially changes in the atoms, and changing the angle at which the light's going to reflect, because you keep changing the shape of the atoms, the direction they're pointing in, their surface, and so you're wobbling, the experiment essentially was sound. But anyway, so what you're really measuring is you're not the real wavelength difference, because you're measuring how much the light has spread is what you're really measuring, and so that's a different line than that center. So that center really isn't just because that's the straight line and that's where the two straight lines match. It's really not. It's made of something more complicated than just a straight line. Everything going straight through the experiment. Because all these paths are a different length. So you are measuring something. You're measuring something that changes with the distance you make the light travel. That changes where these wavelength lines are. But the wavelength lines are longer, which means the notches are further apart as you spread the light. So it's really not a wavelength of light that you're measuring anymore, because you're measuring something that traveled a longer distance. It's a longer line. Okay. Longer line with the same notches on it. So it's just not as accurate as they think it is. It's not as precise an instrument as they claim. Alright, take a little break and then we'll talk a little bit about energy. Probably go back to the blackboard. Alright, conversation about energy. So what is energy? So the Sabine Hassenfelder did a video on it, and I'd play it, but it's just mush. It doesn't really get to anything. And I think it does mention Einstein's E=mc squared, some idea that matter has something to do with energy. But that's only in the form of matter as an atom, let's say. So, I can just, I could draw you a universe. I could say the universe was just the force, right? And so the forces are just traveling, little bits of stuff flying around in a universe. And you could say the universe had a shape, and you could just make it a circle, and you could just have stuff bouncing around, blah, 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 forever and ever and ever and ever and ever. And, as pointed out many times, even if it was hard stuff and it bounced off of each other, bouncing, reflecting would look the same as going right through. It's just about something would leave going one way and something would leave, I can't see that. Yeah, cut off part of the circle. If I had two things crash into each other, going this way, if I make them go through each other, one's going this way, one's going this way. If I make them reflect off each other, one's going this way, one's going this way, you could never tell the difference. So that doesn't look like energy. Now, I'd say that's energy. There's stuff moving, but it's not doing anything, right? So then I have the idea of an electron, let's say, and I say, well, that's matter, okay, by definition. Now, but again, I'm saying Einstein's formulas really has to do with atoms. Atoms, it's E=mc squared, but an electron all by himself, there's no energy. It's not doing anything. It's just sitting there. Nothing. It has to be moving, and to be moving, it had to be, the force has to be pushing it, is the argument. And if a force isn't actively pushing it, it's not moving. So, that's the energy part. So the energy is, you're saying, okay, there's a certain amount of energy in the universe, you could say, and so at any one moment, okay, the electron is going this way, or it's going that way, or it's going this way, or it's going that way, But at any one moment, it can be the moment where it's standing still. The transition from going this way to going that way has in the middle of it not going either way, zero. So there are these times when it's still zero, that it's not being constantly moved by a force. It's just doing nothing because it just got finished doing something and it's resting. So that wouldn't be energy. So there's no, these things really just don't work as arguments to sit there and force it. As a generalization, E=mc squared. Because as a generalization, the only way you can have an atom is you have to have these little bits, electrons and protons, in relationship to each other, and the relationship is full of energy traps, you could say, where energy is going through things and by things and connected to things and is essentially trapped. So the argument is if you take this elemental function of stuff moving, whether it's a force or it's matter, you can understand that if whatever the stuff is I have moving, I can start off with something in balance. There's just as much going this way as going that way. But it's pretty easy to understand that, well, if I create a rule that allows the energy to turn direction, to change direction, then, I can create systems. Obviously stuff could come in this way and go that way, and so it would all be equal if it was just one thing. But if I put two of those things next to each other, then I can end up, you get the idea, I can convert something going that way into something going this way, and then I can convert it again by just putting another thing here and another thing here, and then eventually I can create a trap, and the energy will just keep going around and around and around and around. The capacity to move. And in that capacity, it moves this one this way, and it moves that one that way, and it moves that one that way, and it moves that one that way, which is all the same. It's just as much going this way as it is that way, as it is that way, as it is this way. So it's not going anywhere. You could argue then that's real energy, and I could put more in any direction. Doesn't matter which direction I put it in, right? I could just keep fueling it with more and more little trapped bits, and but all I have to do is, to release it in one direction, is just remove one of those pieces. I just take one of those pieces away, and then everything, the stuff that came in this way, the stuff that came in all these different directions, all of it goes out this way. So you can sort of understand that the idea of what energy is this idea of it's a direction, and that what the matter is doing is changing the direction. It's saying stuff comes in this dimension, it goes out that dimension. It comes in left, it goes out up. It comes in down, from down, and it goes out towards. So if you change the direction of it, you can understand that pretty soon you're going to have a pretty imbalanced universe. Now, the argument would be is it's, just by chance, there would be just as much stuff being trapped going this way as going that way, as going that way, as going that way. But you can also understand that in certain locations of that system, there'd be a lot of stuff trapped this way, and so there'd be a deficit of this way over here, and there can be too much of that way over here, and you can have all kinds of imbalances built in to locations, specific locations, because every time you did this trapping thing, or every time you were pushing an electron, it means that some force wasn't getting where it was going. So it means you've changed the universe in some other location. And that's what we're doing. You're sitting in your chair, but you're really changing the universe for some star millions of miles away. Its universe is subtly changed because you're affecting forces that were heading that way and aren't going to go that way because you're blocking them. You're going to absorb them and you're going to redirect them. Your atoms are going to cause some kind of stuff, and maybe your atom's just going to trap that force as a little piece of its molecular energy, and it'll just be inside those atoms, and then someday somebody might break those atoms and release all that energy that was trapped. With the relationship between these things. Now, I'd argue what makes it even a little more complicated is this whole charge effect, the fact that electrons are different than protons, and that they are interacting with two opposite components in the actual field of energy itself. The energy has an electron bias element and a proton bias element, which changes the dynamics a bit, because sometimes the force is moved in terms of what dimension it's traveling in, and then sometimes it's actually just occupied pushing an electron or a proton. And while it's occupied pushing it, it's not moving as fast as it would have, and therefore again is changing the universe for something that's looking at it. So if I'm watching something moving towards me, I'm really watching it absorb energy that isn't getting to me because it's moving it towards me. But again, that energy theoretically could come from some other direction, a direction that wasn't going to affect me. Okay, so motion itself doesn't cause gravity. Only motion that was caused by you absorbing energy that would have hit you does it cause gravity. You know, which is it's an important distinction to make. And so, so talking about conservation in this complex system is kind of defeating, because there's until you take a really big overview and say, let's look at the whole monstrous system, well, what's going on? Well, let's say that it's a bubble and all the energy bounces off the inside of the bubble and bounces back in, so that can be conservational. All the energy has to come back, and so then you could say, well, then this stuff can get closer to each other, and then it can get further away from each other, and it can oscillate, and it can do all kinds of things, but you can't really destroy any of it. But in some sense, the more matter you have, the more electrons and protons there are, what you really have to be doing is slowing it down some. So regardless, the system, the energy itself, isn't going to do as many things in the universe. It's not going to go as many places. It's not going to travel as far if it had to move matter. So that would be the simple argument that can't be conservational. So in that sense, the universe matter has to be cold, in the sense that it's using up the heat to move. But you could say that in a sense you're not going to be able to see that lack of conservation, because you can't see force that doesn't interact with matter. You can't know of its existence until it does interact with a piece of matter. Watching matter move is the only way we can understand energy. We can't understand it by just, we can understand it. I mean, you can understand gravity exists, and it's a real force, and it's really affecting things, and it's there whether you're there to catch it or not. But I just mean you can't understand it in a conservational kind of way. You can know that when you throw something up, there's going to be a force that's going to slowly slow it down. An opposite force, a force going the other way that's very gently, without it even knowing it's happening, is going to be taking away its motion. It's going to, I don't know how to say it. It's just going to put it back to not moving, being not occupying energy, not using force. Anyway, so it's not a subject. The word energy, I guess, is just too ambiguous to be able to qualify it in the terms that people are attempting to qualify it in. I mean, you really, like I said, really just depends on what you're calling energy. Is energy the amount of movement in the universe in terms of the amount of force in the universe, or is energy when matter moves? And either way, it's hard to make it conservational in the sense, again, because you change the universe by changing the position of matter, and in that sense, it's never conserved, because change means a difference, an imbalance. So it's inherently imbalanced. But anyway, that's probably enough. I mean, so until I can put it in more explicit terms, it's sort of an incomplete subject. I would say, just as a certainty, what I can know is if we quantize the energy, if we say an arrow moving, a little bit of momentum in the universe bouncing around is energy, we know it's going to lose some of that energy every time it moves a piece of matter, in the sense that now it has less potential to move another piece of matter. But the opposite argument would be, see, this is where it gets complicated. Every time I move a piece of matter, I move it closer to another piece of matter. So if there was no other matter in the universe, if there's just one piece of matter, and you did actually have an imbalance in the system somehow, I don't know how, and you actually did move it to another position, you'd have to concede that there's a tiny bit less energy in the universe, because this isn't going to affect any other piece of matter. So the fact that it changed its position, see, if electron goes from here to here, can't make any difference if there's no other electrons to know it got closer to me and created more pressure. But if I move it into another electron, if there's another electron to move it into, there's an electron here already, and then I move this electron here, that's going to mean that these two electrons are going to build up more pressure, and so there's going to be this opposite thing happening, and so that's real conservation, in the sense that you have a conservational push the opposite way. But that's only because you have more matter. And then if you take this system as a whole, it still didn't really change anything. This whole area of space, if there's no other electrons for this whole area of space to affect, you'd still have to argue that less energy came out of this place than went into it over a period of time. That's the force was diminished in its speed, its momentum, a tiny bit by pushing an electron here and then pushing this electron over here. That used up something. Yeah. Anyway, so it's just that, there's so many little bits and so much of it that it's kind of hard to account for all of it. And to say that if I spread all of the units of matter evenly throughout the universe and then applied the energy, would every unit of the universe remain just as active or have just as much force in it? And the argument clearly would be no, it can't. I mean, but maybe it's I guess it depends on how perfect the geometry is. So I guess the argument underlying this is that the universe probably doesn't have enough there's enough imperfection in the geometry that you're going to have all kinds of places where there's less or more. But anyway, yeah, it's just there's not complete enough vocabulary to have a complete enough conversation about the ambiguous terminology of energy. Something like that. Not yet, anyway. Alright, so enough of a video, I suppose, and such. Just disappointing. I really have to get my opportunity to show people, okay, more people, better people. Obviously, sorry, no insult intended, but I need better people to counter-argue, or to at least concede, either argue or concede. And yeah, I need a bigger audience so I can prove that this physics has to be accounted for. This counter-argument is good, and it deserves to be addressed by physics, conventional notions of reality. But it can't be. All they can do is run from it. So again, $1,500 to any channel with more than 100,000 subscribers. So Ken Wheeler, all of these science channels, $1,500 for give me the opportunity to interrogate you in front of your audience, just so I can demonstrate to them that you're being duped and fooled by a fable. And real physics is quite attainable and easy to understand. Enough of a statement, I suppose. So, till the next time, I just have to keep doing this endeavor to persevere thing. Really annoying. Yeah, I hate it. Spent my whole life endeavoring to persevere. So it's like fishing in crystal clear water, and there's just no fish in the water. I mean, shit. you know. Anyway, till next time. Such. Doing it forever. Ugh.